Hi, everybody. Mr. Wagner and I thought it would be a good idea for you to have a recording of maybe one or two extra examples of making these Lewis dot structures for molecules. So here I'm going to demonstrate how we approach this for combining one hydrogen atom, one carbon atom, and one nitrogen atom to make this molecule HCN. So to start off with, what we have to do is go to the periodic table and figure out how many valence electrons each of these atoms has. So I'm just going to start annotating the slide here. So we know that, we look at the periodic table. So hydrogen is going to have an atomic number of 1. Carbon is going to have an atomic number of 6. And nitrogen has an atomic number of 7. So then, when we're looking at the valence electrons that each of these has, now hydrogen, it's in the first row here. So we know that it doesn't have any core electrons. It's the one electron it has is going to be a valence electron. Carbon and nitrogen, they're in the second row, and that means that each of them, they actually have 2 core electrons. So we have to subtract those 2 from the atomic number, which means that carbon has 4 valence electrons, and nitrogen has 5 valence electrons. So one thing that I'm actually going to do now is the next step, which would be to add these up. So the total number of valence electrons that we're going to have is 1 plus 4 plus 5. So that means that there's going to be 10 total valence electrons in our model. And I'm just going to abbreviate valence electrons with VE. So hopefully you can follow along with that. All right, so the next thing we have to do is start making our model. So we need to make Lewis structures of each of these atoms, our hydrogen, carbon, and nitrogen atom. So let's do that. Say that's going to be a hydrogen atom. That's going to be a carbon atom. And this is going to be a nitrogen atom. And make a little bit of space there. So it's going to be hydrogen. So this is going to be carbon. And I said this is going to be nitrogen. I'll move that over, give a little bit more space here. And now we just have to complete the Lewis structures of each of these atoms by putting our valence electrons onto them. So hydrogen has 1 valence electron. I'm just going to put that right there. Carbon has 4. So I'm going to put 1, 2, and remember, we start off by putting these single electrons in each of these 4 positions before we start pairing them up. But carbon only has 4, so we're going to stop after the 4th electron. Nitrogen has 5, so we're going to follow the same pattern. We can put 1, 2, 3, 4, and now we have this 5th one, so we have to pair this. Whoa, whoops, that was bad. So yeah, we have to pair up this last one. So we'll just put it right there, and I'm gonna move these over a little bit, make it look pretty. Okay, so now we have our Lewis dot structures for each of these individual atoms. So the next step is to make sure that the atom that can form the most bonds is in the middle. In this case, when we look at the number of bonds an atom can form, that corresponds to the number of single electrons that we have. So hydrogen has this 1 single electron, carbon has 4, and nitrogen has 3. So that means carbon can form the most bonds here because that can form 4 bonds, one with each of these single electrons. And it's in the middle, so we're already good there. So now we're just going to show how these are going to interact. As we make these bonds, these electrons are going to pair up to make covalent bonds. And that's kind of the definition of a covalent bond, as we make these electrons pair up and then they get shared between the atoms in the molecule. So we can draw a dotted line between the hydrogen and the carbon there. We can draw a line, say, between these 2 electrons on the nitrogen and the carbon. Now we've got these unpaired electrons here, or single electrons here, so we can also draw a line between these. And now you see carbon, it still has 1 single unpaired electron, and nitrogen has 1. It's over here. It's going to be kind of difficult and ugly to draw that line. So what I'm going to do is, I'm just going to move this electron over here. So instead of this pair being on the top, this pair is on the side now. And then that will allow me to draw this interaction between these 2 electrons here. So if we do that, then we don't have any more of these single unpaired electrons. These are all going to pair up. So now the last thing to do is just draw the final molecular structure. So I'm going to move this arrow over here just to give me a little bit more space. And to draw the final molecular structure, so we can drag our elements over here. So that's going to be a hydrogen. Whoops, that was the wrong one. That always happens with these. Okay, oops, this is going to be our carbon. Come on. It's going to be our carbon. I better move that over because it's going to be in the way. And then finally, we're going to have our nitrogen on this side of the arrow. All right, fantastic. There we go. And I can actually give myself a little bit more space here if I want. Okay. So now remember that when we're drawing the final molecular structure, we can replace each of these electron pairs that form with a line that indicates a single bond, a single electron pair. So we'll put a line here between the hydrogen and the carbon to represent these 2 electrons. And then between the carbon and the nitrogen, we're going to have 1 line to represent these 2 electrons. That one's pretty straightforward. But then we're also, that's not quite straight, close enough, but then we're also going to have a line for this pair of electrons. Put that up here. And it doesn't have to correspond to the tops here. We just draw these lines between the atoms. So when we are drawing these multiple bonds, because now we've got 2 bonds between the carbon and nitrogen. And then finally, we have to add the 3rd bond for this pair of electrons at the bottom. So let's just go ahead and do that. And now we've actually got a triple bond between the carbon and the nitrogen. And then the last thing that we do in these final structures is we can't forget about this pair of electrons here. It's not involved in any bonds, so those are non-bonding electrons. We will also call that a lone pair of electrons. So we just have to put those 2 electrons there, and that should complete our model. Now the last step we do is we check 2 things. Number 1, do we have the right number of total valence electrons? Make sure we didn't forget anything. So for example, we had 10 total valence electrons that we should have. Now each of these lines, each of these bonds, that contains 2 electrons. So we have 2 here, that's 4 electrons, 2 there, 6, 8, and then we have these 2 in this pair. So we have 10 electrons. So we can check that off, that's good. And then the last thing we want to look at is the number of valence electrons that each atom has now, given that we have electrons being shared. So remember, these shared electrons, they count for both of these atoms. So the 2 electrons on this bond right here are going to be shared by both the hydrogen and the carbon. So when we count the electrons on the hydrogen here, and I will just get out my annotate tool again. So the hydrogen is going to have 2 electrons from this bond. And if you remember with hydrogen, with 2 electrons, then its valence shell is full. It can't hold any more. And that makes it very happy, satisfied, stable, whatever word you want to use. But that just means it's a good number for hydrogen to have 2 valence electrons. Now carbon and nitrogen, because they're in the second row, their valence shell, if you remember, can actually hold up to 8 electrons. So when those valence, when carbon and nitrogen each have 8 valence electrons, they are happy and satisfied and stable as well. So if we count that, carbon has 2 from this bond, 2 from that bond, 2 from that bond, and 2 from that bond. So it does, in fact, have 8 valence electrons. And then when we look at nitrogen, we get 2 from this bond, 2 from this bond, 2 from this bond, and then finally 2 from this lone pair here. So that's also going to have 8 valence electrons. So everything is happy, everything is satisfied. All of the valence shells, we call them, are full. So it looks like we've got a good model here for HCN. Thank you.